Say we had a continuous function of time, x of t equals u of t minus 3. So that's just a step function. But the step function is delayed by 3 seconds. It means the step function only initiates when t equals 3. So if I set t minus 3 equals 0, that gives me t equals 3. That's where the step function actually starts. Okay, so that's my signal in the continuous time domain, and I'm told that this signal is now sampled. So I'm given the sample rate, and I need to re-represent this as a discrete time function. So I want to write this as a function of discrete time. So to do that, I need to replace t with nt, where uppercase T is my sample period. So T, or Ts, is 1 over 2. So it's the reciprocal of the sampling rate. So we simply replace every instance of T with nt. And now, because we know the value of uppercase T is just half, I can now just replace that T with half. So we have n over 2, n over 2. And I can now replace the brackets with square brackets. And this is now my discrete time expression. And I no longer really need this. So x of n equals u of n over 2 minus 3. And if I wanted to plot this, to represent it graphically, I just want to know where does the step actually initiate. So we know it initiated at t equals 3, but what does that mean in n? So if you, again, you do the same thing, you say n over 2 minus 3 equals 0, that means n equals 6. So it initiates at n equals 6. So what does that mean? We had our time variable t, now we have our new discrete time variable 0. So it's variable n, sorry. That starts at 0, then you'll have 1, 2, 3, 4. Why did I put 1 there? Because my sampling period is half a second. So that's half a second there. That's 1.5 seconds, 2.5 seconds. This is my time axis. And what I'm trying to do is to sketch the discrete time axis, which is n. So 4, 5, 6, 7, 8, 9. So remember, n multiplied by uppercase T, that's T. So n equals T over T, or 2 times T. So again, here you'd have minus 1, minus 2, minus 3. And now I can represent these samples. Let me just do that. I can represent these samples as values. So it's a unit step. So all of these values from minus infinity until n equals 6, all these values should be 0. So 0, 0, 0, 0, 0. At n equals 6, I should have a 1, at 7 a 1, 8 a 1, 9 a 1, etc. And what you can then do, you don't have to, but this is convention, is to add stalks to these. So each of these is now a discrete sample in its own right. Okay, so that now is my discrete time n. So for each, let me just make that a little bit clearer. So this time here, that's Ts. So when n equals 4, for example, that means that the amount of time that's passed is 4 times TS. So what we've now done is we've represented a time domain signal here, a continuous time domain signal here. We've represented it as a discrete time signal here. And we've also sketched it, we've superimposed the sampled sketch or the discrete time sketch on top of the continuous time sketch.